Let me get started then, and it's my pleasure today to introduce Ana Maria Ray, who's a fellow at JILA and adjunct professor at the University of Colorado Boulder. Her work specializes in topics at the intersection of AMO, condensed matter, and quantum information science. Just to give a little history, Ana Maria began her studies at the Universidad de los Andes in Colombia and then moved to NIST in the University of Maryland for her PhD. And that work was awarded the DEMOP Thesis Prize. It was one of the first thesis prizes that I ever heard of. So I think that might have been the first time I heard you speak back when I was a student. Since then, she completed a postdoctoral fellowship at ITAMP and then moved to Boulder and into the positions that she holds now. Ana Maria has received numerous other awards and recognitions, notably the MacArthur Fellowship, the Maria Goeppert-Meyer Award, and her election as an APS Fellow. So I'm really excited to hear her talk today on optical lattice clocks, and I encourage you to ask lots of questions using the Q&A tool here in Zoom and also on YouTube if that's where you're watching it. So Ana Maria, please take it away.
Okay, Lindsay, thank you so much for the very kind introduction. I want to start by thanking the organizers of BAMOS to give me the opportunity to speak today at this seminar series. I want to use this opportunity to describe what for me is the fascinating idea of how atoms and light can be used to create atomic clocks, the most precise timekeepers you have ever imagined. I'm going to go through the inner lockings of the clocks, explain you how they work, and hope I can convince you that atomic clocks are not only fascinating, but important since are helping us to unravel big mysteries about the world and to build next generation of quantum technologies. With that, let me start my talk by acknowledging my collaborators and the people that really do all the calculations and work that I'm going to present today. I'm going to start with my theory group and the names that I have highlighted here. And of course, this work has been done in very close collaboration with Jun Ye, Strontium Optical Lattice Clock at JILA. Actually, Jun is the clock maker and the great group of students, postdocs that have contributed to these great experiments. And of course, the funding agencies for support to this work. All right, so we are talking about ultra-cold atoms, and we know that one of the fascinating opportunities that these systems offer is the possibility to allow us to explore the quantum world. So what are the fantastic opportunities? Well, they might not allow us not only to use the properties of real materials that exist in nature, but instead the design in the lab synthetic quantum materials with properties that surpass the capabilities of real ones. For example, we might be able to build a room temperature superconductor. Also, hopefully they are going to help us to build the technological promise of quantum computers and take all the capabilities to generate really important technological advances and understand the quantum world. But also at the fundamental level, we want to actually be able to connect the behavior of the microscopic world that is ruled by quantum mechanics with the behavior of macroscopic objects that are ruled by general relativity, and trying to understand and connect these two different fields. And finally, one of the great possibilities is try to use these systems to build the most precise sensors that we have ever imagined that can surpass the capabilities of any classical analog that we can build. So ultra-cold atoms offer a potential to connect to all these different fields, but in particular, I'm going to tell you today about atomic clocks that I think they are really offering unique opportunities and advancing the field in all these different exciting and fascinating directions. So with that, let me start by introducing a clock. Of course, a clock is something that ticks in a repeated and regular manner and that we use to count time. And well, all clocks are made of two components, an oscillator, that is what ticks, and the counter that allows us to record the oscillations, actually keep track of time. And of course, clock has played a major role since the existence of mankind. Today, the clock that I'm going to introduce you is an atomic clock that also have two components. In this case, the oscillator is an electromagnetic source. A light can be microwave of optical, a laser. And what counts the oscillations are the atoms. So these are our counters. They are great because they are universal and therefore they are not going to introduce errors, mankind errors that any others. And moreover, in many situations, the oscillations that we are going to keep track of are so fast that even electronics cannot track them. So atoms are allowing us to be the resource that counts these very, very fast oscillations. So as I said, atomic clocks are very important in the sense that they are universal and they are based on the fundamental principle of quantum mechanics, that is the energy splitting of internal levels of the atom that are the same here or in China. I mean, this splitting is universal. And in fact, this provide an unrivaled definition of the seconds. And as we know, since 1967, the definition of the second is based on the energy splitting of the two internal levels in cesium atoms. The second is in fact defined as approximately 9 billion periods of radiation of light associated to this transition. So, of course, clocks, even though the definition of the clock was introduced in 1967, actually clocks started before. In the first clock was built in 1955, again with operating with cesium atoms by Essen and Parry. And since then, there has been fantastic progress and development year by year on building better and better clocks. But of course, the other point that I want to emphasize is that nevertheless, nowadays, even though we use cesium to determine the standard of the second, the precision of the cesium clock is currently not the best in the world. And associated with that, why? I can give you a very, very simple picture. If I show you these two rulers and I ask you which ruler is more precise, of course, you are going to say, well, ruler B is better because it has more ticks and therefore better resolution. And similar things happen in clocks. It happens that the cesium clock operates with microwave that have gigahertz energy spacing, and there are 4 orders of magnitudes slower that we can get with optical transitions. That is that we use for operating optical atomic clocks that are of the order of 100 terahertz energy. So much more faster ticks and therefore better resolution. So in fact, if I'm going to introduce you how the clock operates, in particular optical clocks, we have the pendulum, that is what ticks. We have the atoms that are going to record the oscillations, and then we need to do a feedback cycle that we are going to log the clock with the atomic transition. So I'm going to explain a little bit of that now. So let's start with the atoms. And well, let me introduce you the atoms that we use. For clocks, there are general alkaline air atoms, that atoms that have 2 outer electrons and therefore they're lying in the second column of the periodic table, although we have other similar atoms, other atoms with similar structure like ytterbium. So today I'm going to focus in actually strontium atoms. And in fact, an additional ingredient that we typically use in clocks is the quantum statistic of the atoms. And in this talk, I'm going to focus in fermionic isotopes. And these have the particular advantage that have a nuclear spin I. In the case, for example, of strontium 87, we have a nuclear spin I that is 9.5, opening the possibility to have 10, at the least 10 internal levels for electronic state, helping us to introduce more degrees of freedom in our system. All right, so let's talk about the intrinsic atomic structure of the alkaline air atoms that make them unique for clocks. The reason is that we have here an optical transition that has 2 very long-lived electronic states. So the 1 is 0 and the triple is 0. In particular, you can see this transition is a J equal to 0 to J equal to 0 transition. So it's dipole forbidden, and it's a singlet to triplet transition and therefore spin forbidden. It's not totally forbidden because we have nuclear spin, but still and that's the reason why we have a transition that has a lifetime that exceeds 100 seconds and a line width that can be associated at as narrow as millihertz. So when you try to characterize this atom in the terms of a quality factor, that is the ratio between the ticking frequency and the damping rate, we will get a factor that is larger than 10 to the 17. And if you think about this, it would correspond to a pendulum that when swing, it will start to swing, it will continue swinging during the entire age of the universe. So that's the quality of the atom that we are using here, and that's why they are the L4 clocks. Now, of course, we have to have good lasers, because if we want to take advantage of the atomic transition, then we really need actually to have lasers that have long coherence time. And in fact, in June's lab, they have been able to advance the construction of cavity settings that are ultra stable. For example, they have a silicon cavity that they can reach coherence times that are larger than 10 seconds, allowing to explore this narrow transition in great extent. So besides that, we have to have atoms, and we have to trap them in order to avoid detrimental Doppler shifts. And for that, what we use is optical lattice. Here I'm showing you a 1D optical lattice that create an array of pancakes where atoms are trapped. The advantage of this 1D lattice is that, well, we can devise lattices that are the same for the ground and the excited state. So these optical lattices are built up at what is called a magic wavelength, where we don't disturb the energy spacing of the atoms because they feel the same trapping potential. So by trapping the atoms tightly, therefore we are not subject to Doppler or recoil shifts, but we are not also subject to star shifts, and therefore we can fully explore the capability or the potential of the atoms. All right, so now in order to do the feedback cycle, typically we use what is called Ramsey spectroscopy. That was invented by Norman Ramsey. He got the Nobel Prize in 1989. And the idea is very simple. So I want to have a laser that is illuminating my atoms with some frequency omega laser that I want to log to my frequency of the atomic transition omega naught. So the idea is that, well, when we illuminate the atoms with this laser in the rotating wave of my Hamiltonian, I have a Hamiltonian that is made of independent atoms, and therefore I have a term proportional to the intensity proportional to the electric field of my light, that is proportional, that says a Rabi frequency, and at the tuning, that is the energy difference between the frequency of the laser and the atomic transition. So the point is that when I start my atoms in the ground state and I illuminate the atoms with the laser, then I'm going to start to introduce a rotation. I apply a frequency, a pulse that is very strong. So mostly we care about the omega SX term. So I apply a pulse for some time, and theta here in this talk is going to be the pulse area that is going to be proportional to, or the Rabi frequency times the time I do the interrogation, and therefore I can orient my spin at any angle in the Bloch sphere. We are going to be interested in this angle theta, and the projection cos theta is going to be associated with the C component of my spin. Then I would let the atoms evolve during the dark time without the laser and accumulate a phase that is set by the detuning, and therefore my coherences are going to see this phase. I'm going to have a precession that is determined by the detuning, and because I want to lock my laser with the transition, I'm going to let the system evolve for some time and then read this phase by applying a second pi-half pulse that transform this coherence into population, and then I can read the population of the atoms, or SC, and with that I can get what is called the Ramsey fringe that has a characteristic phase. That is where I try to use to lock my laser to the clock, and then I also want to have very long contrast to measure as long as I can and get a better information of this locking between to get a better locking between my laser and the transition frequency. Okay, so this is perfect. This is perhaps a good introduction of what perhaps all of you are familiar with. But one of the points, or the reason why we want to use clocks operating with neutral atoms, is the fact that we can interrogate a large ensemble. So, but however, this is the dilemma. So we want to use neutral atoms because we want to trap many atoms and have larger signal to noise that grows with the square root of n for incorrelated particles. But the problem here is that atoms collide. And when the atoms collide, they are going to change the frequency depending on the density of the ensemble. And this is terrible for clocks, and we want to avoid as much as possible that. So there is a compromise between these two, and the idea that Jung came or he wanted to use is the advantage of quantum statistics. Why? Well, he wanted to use fermions for the following reasons. If we try to characterize collisions in quantum mechanics, then we can describe the collisions in terms of a scattering problem, where we can describe it in terms of in terms of partial waves that has a quantized angular momentum L. So, because we are talking about the scattering problem, the particles come, collide, and then separate. So after the scattering, they don't feel any potential anymore, and the only consequence of the collision is a phase shift. So this phase shift can be described by a single parameter for a given partial wave. For the case of L equal to 0, the lowest angular momentum states, the S wave, the density shift is characterized by the scattering length. And for the case of L equal to 1, that are the P wave collisions, they are characterized by the scattering volume. So yeah, I try to show here the potentials that are characterize this collision, and the important part is that the L wave, as you can see here, there is a K square. For the P wave, L equal to 1, there is a centrifugal barrier that suppresses the collisions, and here is where statistics also play a fundamental role, because for identical fermions, the Pauli exclusion principles prevents them to collide via S wave, because they will have a symmetrized spatial wave function, and this cannot happen. So the low energy collision channel that is allowed for identical fermions is the P wave channel that, as I said, costs energy. In the case of strontium, the centrifugal barrier is of the order of 30 microkelvin. So we thought that by operating with fermions, we could remove and suppress the detrimental collisions. In this case, just for your information, because we have ground and excited atoms, there are 3 different potential collisional channels in the P wave between ground atoms, excited state atoms, and ground and excited. All right, so nevertheless, after building the experiment with fermionic atoms, back in 2008, Jung discovered that the clock was so precise that collisions were giving rise to him to the second largest systematic in the clock. They were in fact detrimental, and that means that if we wanted to get a better clock, we really need to understand the interactions. So in order to do that, we have taken advantage of the fact that these interactions are weak. So basically, imagine that this is a single pancake of the optical lattice when I have my atoms trapped. And of course, the atoms are not localized, they're moving. We have a system that typically operates at 1 microkelvin, and therefore we have atoms that are mobile. But the important point is that the interactions are weak enough that if I assume that my particles are non-interacting, and because of that they occupy the characteristic single particle eigenstates of an harmonic trap that are characterized by as a quantum number nx and ny, and therefore these levels are quantized. And the important point is that the energy splitting between levels is the order of the trapping frequency that is large enough that collisions are not able to introduce mode changes. They are penalized with an energy cost, and consequently, we are going to assume that the atoms are going to be pinned in these single particle levels, and therefore I don't have to worry about these motional degrees of freedom. So I can write instead a Hamiltonian where the atoms are frozen in these single particle energy modes and instead act as a quantum magnets, because the only thing that collisions can do is to do flip-flops or introduce magnetic interactions, spin-spin interactions. The energy lattice is different than a position lattice, because even though collisions are contact for atoms, so they have to bump into each other to collide, in this energy space, the wave functions are highly delocalized, and therefore there is going to be a large overlap between the momentums in different sites in this energy lattice. Something that is delta function in position can be very delocalized in momentum. So when I write an spin model, then in the spin couplings are actually very long range, and we can think of an almost collective Hamiltonian in great extent. So I can write a Hamiltonian instead of worry about what is the spin of a single atom. I can worry about the collective spin. So for example, I write collective SC. And in this case, for example, the collective SC, it tells me information of the inversion of the number of atoms in the excited minus the number of atoms in the ground state. As I mentioned, it was set, for example, in the times of Ramsey spectroscopy by the first pulse. So when I write the interaction Hamiltonian, I don't going to provide the derivations, you have to believe me, but the interaction Hamiltonian can be rewritten in terms of two interacting terms besides the tuning, the single particle detuning. There is a term that is the form K high SC squared, and there is a term that is proportional to Cn SC. So the important part, well, this chi and C are p-wave interaction parameters. And if I look at the mean field level, so I'm going to try to understand how interactions are modifying the ticking of my clock. You can see that I can factorize this term and having as a term that is proportional to the expectation value of SC times SC. And therefore, when you can see from here, there is going to be a modification of the detuning that is determined by the magnetization along the Z direction of the gas. And this is going to be set in Ramsey spectroscopy by the pulse area of the duration of the first pulse that is set by cos theta. So when we use this model and try to understand the density shift, this is the vertical direction, as a function of the excitation fraction, that is the number of atoms, depends on the pulse area, we see a linear dependence in the experiments. The experiments are the solid lines, are the symbols, and then compare with the theory, that is the solid line, and we see this beautiful linear dependence that was very exciting because allows in principle to place the clock at this point where collisions are not important. So this, in this case, we were able not only to actually use these measurements to determine the peak wave interaction parameters, but also to operate in principle at a sweet spot where density shifts were not important. Of course, there is still one element that I have not mentioned, that is atoms in the excited state can interact via p-wave interactions and join inelastic collisions, and after these collisions the atoms were lost from the trap, and unfortunately they were detrimental, and with them, even if we're operating at this point, we didn't have as long times as we would like to. But anyway, understanding the collisions and other systematicals the clock allowed June's group to actually build a clock that in 2014 was almost 3 orders of magnitude better than the cesium standard. That was fantastic. So this clock has had a fractional uncertainty at the level of, at the 10 to the minus 18 level. That means that this clock neither gain or lose a second in 15 billion years, roughly the edge of the universe. That was fantastic. What I'm going to tell you today a little bit more is that this year we have been able to improve the sensitivity of the clock by other 3 orders of magnitude. And I will tell you a story how we have been able to do that. All right, so, and I think one of the important connections that I want to emphasize is the synergy between precision metrology and many-body physics, because is that by understanding the many-body physics of the system allow us to get better clocks, but also better clocks are going to allow us to resolve a brewery of energy levels that we don't understand in a many-body system into very well-resolved spectra that we can understand, and therefore advance our understanding of complex quantum systems. So in fact, if you try to imagine what makes the understanding of strongly correlated materials very difficult, is actually the interplay between orbital spin and charge degrees of freedom. And the interesting part is that in an alkaline air atom like strontium, we can have all these degrees of freedom at the same time. We have an orbital degrees of freedom, the 2 clock states, the spin degrees of freedom, because we have the nuclear spin, as I mentioned. And as I'm going to tell you now, we can actually make my atoms that are neutral behave as charged electrons. So before going into this direction, I'm going to stop and ask you if you have any questions.
Yes, thank you so much. There's a few questions. So I'm going to start with some that are a bit more technical, maybe. Can you comment on the advantages and disadvantages of using strontium as an active frequency reference, like a super radiant laser versus the passive frequency reference you described in your slides?
Yes, well, of course, at some point, I mean, the super radiant laser is a fantastic opportunity, and there is great progress toward that. I mean, in principle, could beat any other laser that we can, a cavity-made laser, but still there is a lot of progress going on. I mean, hopefully it will happen, but is building a super radiant laser that is continuous is at the heart of many investigations that we are making at JILA. And well, I think if I can say, well, this would be fantastic. No, we are not that there yet, but hopefully soon.
Sounds good. Another question is that you introduced Ramsey spectroscopy in your talk, but a lot of optical lattice clocks seem to opt to use Rabi spectroscopy instead. Can you comment on the advantages and disadvantages of these different sequences?
Yes, yes. Okay, this is something interesting. Well, the advantage of the Ramsey spectroscopy is that you don't have the laser on during the interrogation, and therefore you are not sensitive, too much sensitive to amplitude noise during the interrogation. So there is one advantage. The challenge of the Ramsey spectroscopy is that you have to lock very carefully the first pulse with the second pulse, and you need to add an active feedback cycle that, I'm not an experimentalist, but according to June, this can be challenging. So I think they have advantage and disadvantage in the data that I'm going to discuss later is going to be with Ravi. But for theories, I prefer Ramsey a lot because I can disentangle I mean, my state is
Yeah,
not changing as a function of time. So definitely
for sure.
Ramsey is better.
I guess maybe following up on that, does it matter which sequence you use to when you're thinking about the interactions between the atoms?
Typically, Ramsey is cleaner to understand collisions. Typically, Ramsey, you are starting I mean, that's why how we were able to characterize things very well, but they can describe with the same framework. So not necessary if you want to see beyond infill effects, that is what we are looking for the future, definitely Ramsey would be better. But
Okay. And then one more question about just a few slides ago is from Bill Phillips. It says, is there a simple way to see why the sweet spot for collisional effects is what it is like not just 50%, but some other number?
Yes, I can give a very simple explanation with this formula. So if you see this, we want this term to cancel completely. So that means if I put a pi half, this is not going to cancel because I have this C. This C comes from the different interactions between excited atoms and the difference between BE and BGG. They are different. They don't have the same collisional channel. So if BE were the same as BGG, DC were zero, it's not zero, it's negative. So that's why we have to go to a little bit larger than pi half to cancel. Hopefully
Okay.
but this is an excellent question, and I will clarify that in a bit better
Okay.
more. Mm-hmm.
Great. Well, thanks for all these answers. Maybe we can move on to the next part of the talk now.
Okay, great. So now I'm going to start a little bit focusing in this part because it's going to be very important in order to our accomplishment of canceling and suppressing completely the density shift in the nu clock. All right, so spin orbit coupling, we all know that is a fundamental concept in nature, is the coupling between the electron motion and its spin. It's a relativistic effect. We are familiar when we try to understand the atomic structure that spin orbit coupling is key. Also, spin orbit coupling is key in solid state systems, and it has been the source of the build-up for spintronic devices, is at the heart of topological insulators. And in fact, there has been prediction that if you put a topological insulator next to a superconducting material, then we can have we can generate what is called Majorana particles, and there could be a key for quantum information, topological protected computers, and in fact, Microsoft, for example, is trying to invest in this direction. So it will be fantastic to understand spin orbit coupling in atoms. And the point that I want to make is that, of course, there has been beautiful progress in other atoms, but in our clock, it's very easy to do spin orbit coupling to achieve. The only thing that we need to do is reduce the lattice depth and allow the atoms to tunnel. Why is that? The point is that we're interrogating an optical transition, and therefore the wave vector associated with my transition is large. Or in other words, the laser wavelength is comparable to the lattice spacing that we use for our magic lattice. In the case of strontium, k times A can be larger than pi. That means, or other way to say it is that when I interrogate my sample, the phase, the laser imprint a differential phase that changes from one lattice side to the next. This phase was not important if the atoms were not allowed to tunnel. But as soon as I open my system to tunneling, then in this case, the atoms are going to experience this phase because they are going to go to a side when the atoms are interrogated with the other phase, and therefore I have to care about it. Now, a way to understand this spin orbit coupling is perhaps also going to momentum space or quasi-momentum space. We have atoms moving in the lattice, and therefore the dispersion relation is a cosinusoidal direction with amplitude set by the tunneling rate, or for J, the tunneling rate sets the bandwidth of my dispersion. And because we had in a magic lattice, is the same for the ground and the excited state. Now the point is that I'm going to eliminate my atoms with a laser. An atom, there is going to be can be an overall shift between the two because of the global detuning. But the important part is that if I go into an atom in quasi-momentum Q, absorb a photon from the laser, is going to promote the atom to another quasi-momentum because momentum has to be conserved, and therefore it has to absorb the momentum of the photon. So it's going to experience a momentum kick, and therefore there is going to change the momentum from Q to Q plus K laser, and therefore that's important. It's flipping the spin when experiencing a kick. The way that we like to understand this theoretically is to do a Keynes transformation to just relabel the momentum, the quasi-momentum, in such a way that the atom in the ground and in the excited state are coupled vertically, so there is a diagonal coupling, but of course this has to be absorbed in the shift in the energy dispersion that we add the phi here. The phi is k times A. So in that case, because the coupling is diagonal, we can understand the physics for an atom in a given quasi-momentum just as a two-level system with an effective magnetic field imparted from the laser that has an X component, for example, from the rabbit drive. And then, however, instead of the detuning, I have a detuning that is going to depend on the energy difference between the excited and the ground state that is momentum dependent because of the spin orbit coupling. And this coupling between the spin and the motion that is direct in this Hamiltonian can give rise, is directly the manifestation of a spin orbit coupling. So as you can see, for a given quasi-momentum, the eigenstate of the system lie in the Bloch sphere in the CX plane under these conventions, and then depending on the quasi-momentum, the eigenstates are going to have a different orientation set by theta q, that is with an angle set by the ratio between the rabbit drive and the energy difference between the states. So we have explored the spin orbit coupling in a clock in the case that we make it very dilute. And in order to do that, what we did is just populate all atoms in the ground state. Then we use the fact that the clock is very narrow, and then we can only transfer the atoms that are almost resonant. So we can see that by doing this procedure, we are selecting only a narrow window of momentum. Then we blow up the remaining atoms, and by changing the detuning, the global detuning, we can determine which quasi-momentum we select. So we can select different windows of quasi-momentum by changing the detuning, the global detuning of the laser. So after selecting a given quasi-momentum Q and prepare the atoms in the excited state because I blow out the ground state, then what I do is that I let the system evolve with a stronger rabbit drive. But now, because the orientation of the magnetic field changes depending on the momentum, I'm going to have different Rabi patterns depending on the window of quasi-momentum that I prepare my atoms with. This is exactly what we saw. This is the exact excitation fraction as a function of the time, and we can see that we have very different profiles. But in a very nice agreement with the prediction of the theory, that is the solid line, the dots are the experiment. So we have seen a spin orbit coupling in a system in our clock. Now let's make our clock a little bit more dense by packing more atoms. Remember, there is a different phase imparted by the laser between different lattice sites. And therefore, if I allow my atoms to tunnel from one lattice site to the other, now they're going to be distinguishable because they have different orientation. Therefore, when I allow the atoms to tunnel, I open my system to detrimental S-wave collisions, and therefore, which are very strong, and this is very bad for clocks. So that was a little bit disappointing, but actually now I'm going to tell you an exciting news, that is Jun opted to now tilt his lattice and make it vertically. And this is the new setup that I'm going to describe, an optical clock that where gravity is along the clock direction, the interrogation direction. We call this clock the Warner-Stark 1D lattice clock. So let me try to explain a little bit what is going on. We have the lattice, we have the gravity, and therefore, when I'm going to tunnel from one lattice side to the next, now I experience an energy cost that is MGA because, well, there is tilt. And therefore, if I want to characterize the eigenstates of single particle eigenstates in this lattice potential, it's going to be a superposition. They are called Warner-Stark states that are kind of localized at a given lattice site, and with a weight on the other lattice sites. This is a Warner orbital localized at a given lattice site, but the weight in other Warner orbitals are set by the ratio J, the tunneling divided by MGA, the interaction energy cost, the potential energy cost, and weighted in the form of a Bessel function. So I'm plotting some Warner-Stark ladders for 12 on 3 recoils, and you see that even at 12 recoils, I have a great degree of localization. Of course, I go shallower, I delocalize more, but in a very controllable way. So the new opportunities that we are exploring here is that we have the interplay between gravity, spin orbit coupling, and interactions. This has allowed us to have the following improvements. We have been able to achieve Ramsey coherence times longer than a half minute by synchronous comparison between the two sides of the two regions in the cloud, because we can operate at much shallower lattices, steam being kind of localized and suppressing undesirable motional decoherence. Moreover, the weakened confinement lowers the local density at a given site, suppressing detrimental P-wave lossy collisions. And furthermore, and that's the beautiful part, that we can control the degree of localization, allowing us to have weak P-wave interactions, but also some degree of S-wave interactions allowed by spin-ordered coupling, and accomplish full cancellation between the two. And that has been key for important developments, not only for exciting developments at the fundamental level, as I'm going to explain, to exploring physics at the fundamental level, but for exploring rich many-body physics. So let me tell you a little bit more about the suppression of density shift in our Warner-Stark lattice clock. So now we go to this localized model where atoms are localized in the single particle orbitals. Now we have harmonic oscillators along the transverse direction and Warner-Stark state along the lattice direction. Now, if I rewrite my Hamiltonian spin model, assuming localized particles, now I have to sum over different lattice sites, not only focusing on a given pancake. You can see that we have local P-wave interactions, same way that I have before. Were always present in my pancake with chi and C0, terms that are on site and set by P-wave collisions. But now, because as I mentioned, there is an interrogation of the clock laser that changes from one light side to the next, I open my system to S-wave interactions. They acquire this form where there are S-waves, so it's stronger, but they are between nearest neighbor sites. So eta 1 are here dimensionless overlap between nearest neighbor sites. And here you can see that phi is the spin orbit coupling angle. If phi is 0, I don't have S-wave. So this is allowing me actually to generate a Hamiltonian where now if I try to look at the mean field level, the ticking of the clock, the tuning is modified by not only the P-wave interaction, but this amount of S-wave too. And we are able to operate at lattice depths where we can cancel this very well. So these are this is the experimental measurements of, this is the fractional density shift per atom as a function of lattice depth. We can see the ratio between S-wave and P-wave contributions to the density shift. And very nicely, we see a very nice spot where I have perfect cancellation between S-wave and P-wave. giving rise to zero frequency shift, very strong S-wave interactions at shallow lattice, weaker but still significant P-wave interactions at deeper lattice where the density is a little bit tighter. And moreover, this at the magic depth, which it depends a little bit on temperature, pulse area, lattice spacing, but we are able to null interactions there. So the nice part is that Jun's group tried to measure the cancellation of the density shift at this magic depth. And over a 10-hour measurement, they observed a frequency density shift that was consistent of below 10 to the minus 21 per atom. So basically canceling the density shift. And now, because we are not sensitive to the detrimental P-wave collisions, we are actually having a coherence time that they are reaching 37 seconds. Well, why is that? With this level of coherence time and nulling all the density shifts, they were able to resolve a gravitational redshift. So we know that clocks at different gravitational potential tick at a different rate. So Einstein taught us that because of general relativity, the fractional change of the frequency depends on 0g, local g, h, the distance from the surface of the Earth, and c squared. And for the air parameters, this is of the order of 10 to the minus 19 per millimeter. So there is an energy difference at a gradient of 1 millimeter. That is the frequency. This is the fractional frequency shift. An experiment at NIST in 2010 were able to resolve such rate shift when they placed two clocks separating at a distance of 30 centimeters. Now, in his clock, Jung was able to resolve the redshift within 1 millimeter sample. So they, over the course of 8 days, they completed 14 measurements. And for each measurement, they have this data here, and they present here the solid line, that is the mean that they calculated, the dashed line that is the standard deviations, and the red solid line is the value that they expected from parameters from air, and then showing that they can resolve the gravitational redshift at this millimeter scale. That is quite exciting. So I am about to finish, but I want to mention that besides this 1D clock, there is also a new generation of 3D optical lattice clock, where there is a 3D lattice that is to confine the atoms. We are talking about 10 to the 4 atoms, but a quantum degenerate Fermi gas at temperature of T over Tf of the order of 0.1, where all the degrees of freedom are quantum. There is only one atom per side in principle, and in that conditions, in principle, there is no density shift, no collisions. We can pack as many atoms as we want. That would be fantastic. And moreover, if we want to control the spin-orbit coupling, is controllable, because if we allow only tunneling along planes by making the lattice deep along the other direction, then what matters is the projection of is the k vector along the plane where the atoms can move. And therefore, this is controllable by orienting the laser orientation. So if the laser is perpendicular, I don't have any spin-orbit coupling. If I tilt it at some degree for the parameters of the clock at 59 degree, we have exactly pi spin-orbit coupling. And this, in the interplay between spin-orbit coupling and interactions, has allowed us to explore how to generate, for example, useful entangled state that could make the clock better. So we have a proposal of how we can generate spin exquisite states, how can we generate cluster states that are very highly correlated states useful for one-way quantum computing. We can also a proposal on how we can use spin-orbit coupling to generate CAD states that could be also good for clocks or for error corrections, opening us so as exciting opportunities. And I'm running out late, so I'm just going to say that I have not told you anything about the nuclear spin, but the nuclear spins also offer a very exciting direction where we can have new type of symmetry in the collisions, because there is a decoupling between the nuclear spin and the electronic spin. There is no hyperfine coupling in this clock state. There is a new symmetry that opens in the collision, that is SUN symmetry, that gives rise to the possibility of exploring exotic magnetism in these atoms. So I will not talk about this in this talk, but of course there is the review that we wrote a few years ago, and now we are writing a new review because of all the progress in SUN physics. So with that, let me finish and say, well, there is a great vista ahead. We have been able to control collisions, but now we are planning to use the control of collisions to actually generate entanglement and generate better clocks. we hopefully can use these collisions also in the 3D lattice clock to start thinking about possibilities of implementing gates and or prospects of quantum computing capabilities in the clock. And of course, there is a slew of opportunities for exploring quantum gravity at some level or understanding the ripples of space and time. And with that, thank you very much for your attention.
Thank you so much, Ana Maria, for a really interesting talk. We do have a few questions in the list here, but I encourage the audience also to use the Q&A to add any more questions that you have. We have plenty of time. So I will get started in the meantime. It's a question from Shimon, it's a bit of detail, but the phase phi that determines the effective flux that shifts the upper band in the spin orbit coupling is set by the ratio between the wavelength of the lattice and the wavelength of the clock laser, and happens to be 7 pi over 6 because the magic wavelength is close to the clock transition frequency. Is this a particularly good value for doing many body or condensed matter simulations, or are there any prospects for tuning that value?
Yes, that's an excellent question, Shimon. And well, June has two approaches. And yes, definitely this is the way to go. We want to tune this angle. So there are two possibilities. Either go to a 3D lattice, and as I mentioned, making the one of the directions very tight, and so prevent tunneling in some degree between these, or use gravity also to further suppress it, and then having the dynamics only in the XY plane, and therefore, depending on how you tilt the clock respect to the XY plane, you can control this angle. And June is trying to build this setup. I mean, it's a little bit complicated actually to lock, because you have to go lock the clock laser respect to the lattice beams, but they are doing, my understanding is they are doing progress in trying to tune this angle and try to achieve these two angles. For us, pi poles, reaching phi equal to pi, it's interesting because we can, in our proposal, generating cluster states, CAT states can be done at this angle. But on the other hand, if you want to really explore chirality, angle phi between pi half could be a very nice angle to explore chirality. The other way that June is also building is an accordion lattice that you can tune the wavelength of the spacing, of the actual spacing of the lattice by interfering the lasers in a different angle, not only propagating along or counter-propagating directions. And June is trying to build this accordion lattice. Progress is going on. I don't know how long it's going to take, but that would be very exciting.
Yeah, be a lot of flexibility with that. A question from Bill Phillips here is, would you describe the relative advantages and disadvantages of 3D versus 1D lattice clocks for clock quality?
That's an excellent question, Bill, as usual. The disadvantage of the 3D lattice is that the lifetime has been limited to 12 seconds at the moment, because light scattering is happening in the clock. I mean, even at this when you want to have a deep lattice, then the intensity of all these different beams along the different direction increase the rate of light scattering, and the lifetime has been limited to 12 seconds. One of the biggest advantage of the 1D lattice is that, of course, it's only one beam, and therefore we can operate at even shallower, with gravity there, we can operate at shallower lattice. But I mean, in principle, combining the 3D lattice with gravity, I mean, there are fantastic opportunities if we can take advantage of all of them. So if you look at the 1D lattice in the context of many body physics, we have many atoms per pancake, and this makes the system a little bit more mean field-like in some degree, because the density is smaller. When we go to the 3D lattice, the density is of course higher. Collisions are detrimental if you don't control them, but on the other hand, you have Fermi statistics that can always help you. In principle, if you have one atom per side in the 3D lattice, Fermi statistics will not allow you to tunnel if there is another atom there. So but if you have holes, then the story is different. So I think it's an exploration. There is a race and competitions, I can say, between these two, strontium 2 and strontium 3. Hopefully that's a good word to use. But yes, currently in the 3D lattice, they are exploring dipole-dipole interactions. I mean, when you have one atom per side in the lattice, the next interactions that were going to kill you, or not kill you, but introduce systematic is dipole-dipole interactions. And now this is what is happening in June's lab.
Very good. Another question from Bill here is, should we think of the uncertainty of several parts in 10 to the 21 as being a measure of the overall accuracy of the clock, or is the accuracy with which one can measure the gravitational redshift, with other errors canceling out because they're common mode?
Yeah, but well, there are other errors coming from AC star shifts that they are trying to control. I think these are going to, I mean, this is mostly on the fractional density shift. So I think, I mean, they have not, this is, I mean, they are trying to control black body radiation, AC star shift. So maybe it's I mean, they have to quantify that better. At the moment, what they're confident is that there are 10 to the minus 21 effects in this for measuring gravitational redshifts. But I think I mean, they're working in a better calibration or other systematics, black body radiation, AC star shift. I mean, yes. So at the moment, it's just for the, as you said, for the fractional density shift and the capability for them to inform a gravitational redshift, that there are cancellation between two parts of the cloud because they are comparing the ticking one respect to the other. So overall calibration of the full system, I think, needs more careful analysis, and is going on now.
Okay. Let's see here. What do I want to hear the answer to? Another question from Shimon is, suppose we want to build one of these world record setting clocks and put it in space. There won't be any gravity to help anymore. Is there anything you can do instead to get the same suppression of tunneling or localization and the magic depth cancellation of the density shifts?
Yes, well, in principle, yes, I mean, I cannot say that is not possible, but because it might be possible. I mean, I am, but if we are able to generate an accordion lattice, perfect accordion lattice, where the spin orbit coupling is zero, then the spin orbit coupling angle is zero, there is no way that the laser is going to introduce S-wave collisions. So you will be limited to P-wave collisions. And in this case, if you really have the possibility to cool down your system and put one atom per side, you can decrease your lattice depth as much as possible, because Pauli statistics will not allow you to tunnel. So you will have a perfect setup where there is no interactions at all. You cannot have P-wave interactions because you cannot have two identical atoms in the same state at the same lattice side. So P-waves are suppressed as long as you are always in the lowest band. And so yes, so in principle this is possible, but you have to be able to use the magic wavelength in all directions, or and create a full band insulator.
All right. Another question is, are there also inelastic collisions that result in the loss of the Varney-Stark clock? Are these also affected by the delocalization across multiple sites?
Well, yes. So we are very lucky that in strontium, EG collisions are elastic. So the only collisions that can happen are inelastic EE P-wave interactions, and P-wave interactions are highly suppressed at lower lattice depth. So they are there here. I mean, as you go to deeper lattice, where, I mean, remember that we are having pancakes. So yes, so at this lattice depth, at deeper lattice depths, P-wave losses are affecting us. Here, the most important losses are coming from, the most important interactions are coming from S-wave and S-wave. It's only have you can only have collisions in S-wave between E and G atoms that are elastic. So that's that's what we are. That's what one of the gains that we have by going lower, that the local density decreases, and we are suppressing significantly P-wave collisions. Up to what level they're going to affect us, for example, at this point, and if they can interrogate for longer times, that's interesting. At the moment, still the fundamental limitation for going longer than 3 seconds, or most of the interrogation, this Rabi gravity measurements were done at 3 seconds of full interrogation. Going for longer, light scattering start to be an issue, and opening the role of S-wave interactions and things like that. So yes, the answer is yes.
All right, I have one more question on the list here that I'll send. Does the linear stark delocalization at weak depths in a tilted lattice still result in broadening and loss of contrast?
Very little, because that's the advantage of the Warner Stark states that are, well, there is I mean, we don't see that much at the moment, because there, I mean, when you have quasi-momentum states, we see a very rapid decay of the Ramsey fringe, for example. At the moment, we don't see too much, and the advantage also is that in some way, the presence of finite S-wave interactions opens also a many-body gap that protects against delocalization in some degree. So the spreading introduces some disorder because it's an inhomogeneous effective magnetic field experienced by the atoms. There is there, but S-wave interactions can help us to protect against this defacing. And at the moment we don't, well, at the theory we don't see them. They're going to be more manifested in when we go and look at Ramsey, that we can see how much it's going to be limited. It's an excellent question. At the moment we don't see it. Let's see how much this delocalization could happen at when they interrogate for longer times.
Okay, thank you. I think that'll bring our questions to a close for now. You've answered many, and been some really interesting work here. And I mean, this is, super fascinating work, just showing us, the ultimate precision that experimentalists can do, and that the theory is able to pick out all of these, effects out of there. So I think we're going to have one quick announcement before we wrap up. There is going to be a discussion following this talk for any students, postdocs, researchers who want to maybe discuss any questions more casually with the speaker. And I'll just, wish everyone a nice break from the semester, hopefully coming up, and a happy holiday season, hopefully in a warmer place than Edmonton, Alberta, where I am. So Shimon, do you want to go ahead and share a slide?
Yep. Thanks a lot, Lindsay, and thanks, Ana Maria, for a really fantastic talk. So really quickly, we just want to announce that this was the last talk of 2021. It was a great way to finish, I think. And we're going on a bit of a winter break. So we're going to also be switching over to make use of more APS resources. So when VAMOS starts back up again, you'll be getting the emails from APS, not from our Google list, our kind of duct tape together rickety systems, but a more polished APS email list, and they'll be running the Zoom webinars, but everything will still work exactly the same. Your experience will basically be unchanged. It's still the VAMOS you all know and love. And so, but to facilitate that change, we're going to take a little bit of a longer break. So we'll be back in early February, and stay tuned. We'll start announcing the schedule and the talks that are coming. And I think that's everything. So happy holidays and happy new year, everyone. And then I'm going to post the link for discussions with Ana Maria and encourage you all to join. Okay.